Quantum mechanics being the physics of the very small, we have to deal with the behavior of very small things. One nuance of dealing with small things is that they're very difficult to distinguish. If I have an electron here and an electron here, there's really no difference between this electron and this electron other than their position. It's not that this electron has a distinct identity from this electron. The analogy that Griffiths uses is that I can't paint this electron red and this electron blue, or hire a private investigator to follow this electron around to make sure it doesn't exchange places with this other electron. And quantum mechanics has to respect that indistinguishability. If we're working with distinguishable particles, we can write wave functions like this. Psi of the position of particle 1 and the position of particle 2 as two arguments to the wave function, being, for instance, the state psi a, the single particle state for particle 1, x1, multiplied by the single particle state psi b for particle 2, x2. This, however, is distinguishable. If I swap these particles, x1 and x2, by exchanging the coordinates where I'm evaluating this wave function, I'll get a different result. I'll get psi a x2, psi b x1, and that is in principle different than psi a x1, psi b x2. What we discussed in the last lecture was that we could construct construct wave functions for indistinguishable particles by making combinations of permutations of these distinguishable particle wave functions. For instance, our distinguishable particle wave functions psi a x1, psi b x2, combined with, either with a plus sign or a minus sign, psi a x2 and psi b x1, will give me the same wave function, essentially, back if I swap x1 and x2. If I swap x1 and x2 here, I'll get psi a x2, psi b x1, plus or minus psi a x1, psi b x2. And that's essentially what we have here, essentially just swapping these two terms. If I use the plus sign, I'll get my original wave function back. If I use the minus sign, I'll get minus my original wave function back. And that minus sign does not affect any of the observables. Changing the sign of the wave function won't affect any of the outcomes of any of the measurements you could make. There is, however, one aspect of these combined particle wave functions where the plus and the minus sign actually make a difference. When we're making indistinguishable particles, the way we choose to make them indistinguishable actually does make a difference. And one way to see see the difference between the plus and the minus signs is to calculate the expected value of the separation of the particles. This leads to something called an exchange force, and exchange forces are really an interesting nuance to quantum mechanics that has no classical counterpart. So let's consider calculating the expected value of the separation between these two particles. So expectation of x1 minus x2, and we'll have to square that, because if these particles are going to be indistinguishable, I can't tell which one is to the left of which. So the absolute difference, or the difference x1 minus x2 expected value, must go to 0. But if I square it, I would expect there to be, on average, some squared separation between these particles. So we can work with this. This is an expected value. You can, first of all, you can expand it out. x1 squared plus x2 squared minus 2 x1 x2. And these are the terms that we're going to be working with. The expectation of the sum is the sum of the expectations. This is a property from statistics, if nothing else. So this gives us the expected value of x1 squared plus the expected value of x2 squared minus twice the expected value of the product x1, x2. So if we're going to evaluate this sort of expression for the expected value of the separation in these indistinguishable particle wave functions, or in this distinguishable particle wave function, we're going to need to be able to evaluate terms like the expected value of x1, the expected value of x2, squareds, etc. Let's consider the distinguishable particle case first. We're working with these terms, and for instance, let's consider calculating just this first term. We're looking at the expected value of x1 squared, and you know that in quantum mechanics, the expected value is calculated as an integral of the complex conjugate of your wave function times the quantity that you're calculating the expected value of times the original wave function, integrating over all possible space. Since we have two coordinates here, I'm going to be doing a double integral from minus infinity to infinity with respect to both variables. I'm integrating dx1 and dx2. And my wave function now, since I'm working with the distinguishable particle case, psi of x1, x2 is equal to psi a x1, psi b x2, just going to be psi a star x1, psi b star x2, my quantity that I'm calculating the expectation value of, x1 squared, and then my original wave function, psi a x1, psi b x2 without the complex conjugates. So this is the expression that I'm working with, and this is very straightforward to work with, compared to at least the typical expressions that we're working with now, or we'll be working with for the rest of this lecture. We have functions of x1, we have functions of x2. The things that are functions of x1, this is a function of x1, this is a function of x1, and this is a function of x1. Likewise, this is a function of x2, and this is a function of x2. We're integrating dx1, and we're integrating dx2. The terms that are functions of x1 don't depend on x2, so I can pull them out of the x2 integral, which means I can split this integral up overall. This is going to be equal to the integral from minus infinity to infinity dx1 of psi a star of x1, x1 squared, psi a of x1. And my integral dx2 is going to look very similar, minus infinity to infinity dx2, with my terms that are functions of x2 in them. Psi b star x2, psi b of x2. Now, you recognize both of these integrals. This integral here, on the right, my integral dx2, this is a normalization integral. So this is just going to go to 1 if psi b is properly normalized. Typically, we're going to assume that wave functions for single particle states are properly normalized here, so you don't need to worry about this. This is just going to go to 1. The term here on the left, you should also recognize. This is the expected value of x1 squared in the state psi a. But since if I'm just considering the single particle state psi a, I don't need to worry about the fact that this is x1 or x2. This is just a coordinate. This is going to integrate out. So I'm going to write this as the expected value of x squared in the single particle state psi a. This subscript a means that we're working with a single particle state. Single particle state a. So this tells me that what I started with here, the expected value of x1 squared in my overall state, just becomes the expected value of x squared in the state a. Essentially, this more complicated expression becomes a less complicated expression, slightly. You can do similar reasoning for the other components. For instance, the expected value of x2 squared in my overall state becomes the expected value of x squared in the state b. And the product, similarly, the expected value of x1, x2 in my overall state breaks up into two separate products for much the same reasons. The expected value of x in state A times the expected value of x in state B. If this were, for instance, x1, x2 here, I would have something that's a function of x1, that this would become x1, and the x2 would appear here and would instead be lumped with the functions of x2, and we just get two separate expectations. Combining these results, what we end up with is that the expected value of x1 minus x2 quantity squared in my overall state is the expected value of x in the single particle state A, expected value of x squared in the single particle state A, plus the expected value of x squared in the single particle state B, minus twice the expected value of x in the single particle state A, times the expected value of x in the single particle state B. That's my expression for distinguishable particles. For indistinguishable particles, we're going to get a different result, but keep this expression in the back of your mind, because we'll get something that looks very similar for the case of indistinguishable particles. For indistinguishable particles, the wave function we're working with is psi a star x1, psi b star, not stars, just my original wave function now. I'm not writing down the integral yet. Psi a of x1, psi b of x2, plus or minus psi a of x2, psi b of x1. This is the wave function we're working with, and it's now a good deal more complicated. We have two distinct terms, and they're combined with either a plus sign or a minus sign. So we're going to have to work with that somehow. The first term that we had to calculate in calculating the expected value of the separation squared between these two particles was the expected value x1 squared in our overall quantum state. As before, this is going to be written as an integral from minus infinity to infinity dx1 minus infinity to infinity dx2. And then we have our overall wave function, which is going to be a relatively complicated expression, unfortunately, since now we have two terms. We're going to have a complex conjugate of this, the quantity we want to calculate the expected value of, times this originally. So we've got to work with some parentheses, and I'm going to introduce some shortcut notation here. I'm going to write psi A1 for, let me make a little comment tag down here on the bottom. Psi A1 is representing now psi sub A of x1. So I'm not going to write the parentheses and the x, just giving you the subscripts. Psi A1 is psi sub A of x1. So this is now going to be psi A1 star psi B2 star plus or minus psi A2 star psi B1 star. That's the complex conjugate of my wave function. The quantity I'm taking the expected value of comes next, x1 squared, and then my original wave function, psi A1 psi B2 plus or minus psi A2 psi B1. This is the integral that we're working with, and we're going to end up with 4 distinct terms, essentially distributing this binomial and this binomial. Thankfully, we're working with wave mechanics now, so all of these things commute. The x operator here, if you're thinking about calculating the expected value of x squared as an operator, is just multiplication by the quantity x1 squared. So this commutes with everything. I don't need to worry about keeping the orders straight. I can shuffle things around that way. That simplifies things a little bit. And what you're going to get when you expand this out for your 4 terms, this is going to be equal to, oh, sorry, I forgot to give you the original normalization here. There's a 1 over square root of 2 out front here. When I have a 1 over root 2 in both of these terms, I'm going to get a 1/2 overall. So we have a 1/2 out front, and then we have our 4 terms. As before, I'm going to split up the terms that depend on x1 from the terms that depend on x2, and I'll end up with 2 separate integrals in each of these 4 terms. The first term is an integral from minus infinity to infinity, which I'm not going to write, of psi star A1, and then, since I'm calculating the expected value of x1 here, x1 squared, and then psi A1 again. So the first integral in the first term comes from multiplying these 2 terms together. So I've got a psi A1 star and a psi A1 and an x1. Those are my terms that depend on x1. Likewise, this is now the integral dx1. The integral dx2 looks similar. I have a psi B2 star, no x2, just x1, which doesn't depend on x2, so it's come out of this integral, psi B2 dx2. So this is my first term, and you know what this first term is. This part is a normalization of psi sub b using x2 as the coordinate, so this part of the integral is going to go to 1. This integral is the expected value of x1 squared in the state, single particle state A, using x1 as my coordinate. So this is going to become x squared in the state A, same as before. This is not the only term that we have here. Another term here, going psi A2 star psi B1 star times psi A2 psi B1. Now we've got psi A star and psi A2 star and psi A2 using x2 as my coordinates. So essentially these terms are going to end up swapping around. These are coming in with a plus sign, since if I use the plus and the plus, I get a plus. If I use the minus and the minus, I get a plus. And my integral with respect to with respect to x2 now, is psi A2 star, this first term here, times psi A2. Still dealing with x1, so now my psi A doesn't have any x2 or x1 in it, and this is now my integral dx2. My integral dx1 now has my psi b's in it, so I've got psi b star psi b1, x1 squared, psi b1, integral dx1. So this is my second term, and it evaluates to the expected value of x squared in the state B. The remaining 2 terms, let's examine them conceptually first. I'm looking at, for instance, this term that comes from multiplication of these 2 psi's and these 2 psi's. And if I work that out, it looks like this. My terms that depend on let's deal with the first part here that depend on x2. I have a psi a2 star, and then I have a psi b2, and this is my integral dx2. My integral dx1, depending on my x1, is psi b1 star x1 squared psi a1, integral dx1. This is an integral dx1, sorry I forgot to mention that. This term here should look familiar. This is a psi a2 star psi b2, integral dx2. So x2 is our variable, and we have essentially an orthogonality integral between psi a and psi b. If psi a and psi b are distinct states, which we're going to assume for now, this orthogonality is going to give us 0. So this is 0. Doesn't even matter what this is. This term goes to 0. The remaining terms, the fourth term, which comes from combining these two, is going to give us psi a1 star x1 squared psi b1. And then for my x2 dependence, psi b2 star psi a2 dx2. And I've left off my dx1 here, and this term goes to 0 for much the same reason. This is an orthogonality integral of psi a and psi b, same as this was an orthogonality integral between psi a and psi b. So this goes to 0. The overall term, again, goes to 0. And what I get is, in the end, that the expected value of x1 squared in this is 1/2 of the expected value of x squared in the state A plus the expected value of x squared in the state B. This makes a good deal of sense. If I have indistinguishable particles, what I get for the expected value of x squared, or x1 squared, the position of the first particle in an indistinguishable particle case, is essentially the average of the x squareds for the case A and the case B. If you follow through replacing 1 with 2 in this algebra, this horrific mess here, you end up with essentially the exact same result for x2 squared. The expected value of x2 squared and the expected value of x1 squared are equal to each other, and that makes perfect sense. If the particles are indistinguishable, the expected value of the squared magnitude of the position of one particle and the squared magnitude of the position of the other particle should be equal. That's part of what it means for these particles to be indistinguishable. So these are the first two pieces of what we need in order to calculate the expected squared separation between these two particles. The other piece is the product x1, x2. We also have to calculate that. So x1, x2, in these two cases, what we got before isn't going to break down quite as nicely into an orthogonality integral. But as before, this is going to be equal to 1/2 of 4 separate integrals. And if you refer back to the previous page, what we're looking at is going to look very similar. And it's going to be, in this case, psi a1 star. And then I've got to have an x1 and an x2 in each of these terms, since I'm working with the expected value of x1, x2. So none of my terms are going to be simple normalization or simple orthogonality. Psi a1 x1, psi a1, integral dx1 times the integral of psi b2 star x2 psi b2 dx2. That's our first term. I'll just continue writing the terms down. Our second term is the integral of psi a2 star x2 psi a2 dx2. Second term for that, dependent on x1, is psi b1 star x1 psi b1 dx1. And then our cross terms, which we considered second in the previous slide, is plus or minus. Just a moment to make sure I didn't screw something up. Going back to the previous slide, yes, I did screw it up. I wrote plus signs down here, where in reality we have plus or minuses in the expression. So I have to correct this to plus or minus. Keeping track of the signs here is important. It wasn't important here because these terms went to 0, but for the case of x1, x2 expected value, it will be important. So, going back to the expected value of x1, x2, plus or minus is what we're going to get in our cross terms. Plus or minus integral psi a1 star x1 psi b dx1 integral psi b2 star x2 psi a2 dx2, and then similarly plus or minus psi a2 star x2 psi b2 dx2. I forgot to write a subscript 1 here. Integral psi b1 star x1 psi a1 dx1. So these are the 4 terms that we get. And as before, some of these terms are recognizable. This first term here is, using x1 as the coordinate, the expected value of x in the state A, single particle state A. This term is the, using x2 as a coordinate, expectation of x in the single particle state B. So this here is going to give us expected value of x in the state A, expected value of x in the state B. Likewise, this expression is exactly the same, but we've swapped x1 and x2 for our 2 coordinates. That doesn't matter. When we're integrating over the coordinates, the result is what we're interested in, not the name of the coordinate that's being integrated over. So again, this gives us the expected value of x in the state A, expected value of x in the state B product. Looking very similar to what we got in the distinguishable particles case. But where things differ is in these cross terms. These terms are not anything that you're familiar with. We have psi sub a of x1 times psi sub b of x1. So this is not an expectation of anything that you're familiar with, but it does sort of look like an expectation. And overall, what we're going to get here is going to be the same for these 2 terms, using x1 as my coordinate, using x2 as my coordinate, x2 as my coordinate, x1 as my coordinate. Comparing these 2 terms together, this is psi a1 star. So this is a complex conjugate of psi a, using x1 as a dummy variable. This is psi a, using x2 as a dummy variable. So if I decided to rename my dummy variable here to x1, I would get exactly the same expression here, but for a complex conjugate. So these 2 expressions are complex conjugates of each other. Similarly for these 2 expressions. The complex conjugate of the left integral is the right integral, up to the name of the dummy variable that's used. So I have here either plus plus or minus minus, either the plus or the minus. No matter what, these 2 terms are going to combine. They're both some complex number multiplied by its complex conjugate, so they're both going to be positive real numbers, essentially squared magnitudes of something. And I'm going to call that quantity absolute magnitude of x subscript a b, so abusing the notation a little bit. This is Griffith's notation. I'm not making this up. Squared magnitude. So essentially we're looking at something that looks like it's in the state AB, though that doesn't really make any sense. It looks like an expectation of some coordinate x, and it looks like a squared magnitude since you've got a number multiplied by its complex conjugate. And we have 2 of these things, so if I combine these 2 together, I could put a 2 out front. What we get, combining the results from this slide and the results from the previous slide, is that the expected value of x1 minus x2 quantity squared is expected value of x squared in state A plus expected value of x squared in state B minus 2 times the expected value of x in state A, expected value of x in state B. Very similar. This now is coming from this part. And then we have minus again from the fact that we're subtracting the expected value of the product. And we have a minus, or a plus or minus here, so that's going to become a minus or plus overall, since we're minusing, a plus or minus. 2 times expected value of x in the state AB, abusing notation, squared. So this left-hand part is our distinguishable particles result. And this is weird. This tells us that whether we use the plus sign or the minus sign in the indistinguishable particles case, we get something different for the expected value of the separation between these two particles. So separation has an effect on distinguishability. Combining our results all together, the expected value of the separation of the two particles, the difference between their two positions, gives you a distinguishable particles result plus or minus this difference. And this expected value in the state AB is an abusive notation, but looking at it like this, it's an integral of psi A star times x times psi B, just treated as a function of x. This guy, if you think about it, if psi A is 0 wherever psi B is non-zero, and psi B is 0 wherever psi A is non-zero, these wave functions don't overlap. This quantity is equal to 0, and the result that we get for indistinguishable particles is the same as the result as we get for distinguishable particles. This integral, in some sense, measures the overlap between these two wave functions. If the wave functions overlap, essentially, you're going to get different results. And what you get here, if I draw this out, let's say this is my delta x-axis, calculating the expected value of this separation. I guess I should label it separation instead of delta x. Our distinguishable particles result is here. Distinguishable particles. If I have indistinguishable particles that I've combined with the plus sign, the plus sign was the top sign in my original combination, which means I'm going to be using the minus sign in my expected value of the separation. So if I have indistinguishable particles here, indistinguishable particles with the plus sign, the boson case, the separation I get is actually slightly less than I got for distinguishable particles. If I use the minus sign, constructing indistinguishable particles with the minus sign, the fermion case, the separation I get is actually slightly larger. Now, I'm hesitating to use the terms fermion and boson here. The key point is that we're using the minus sign and the plus sign in the spatial wave function combination to render the particles indistinguishable. These particles, with the minus sign, the essence here is that they're asymmetric under exchange. The spatial wave function flips sign when I exchange the particles. Whereas here, the spatial wave function does not flip sign when I exchange particles. So, if all we had is a spatial wave function, the minus sign would represent fermions, and the plus sign would represent bosons. And you know, of course, that spin complicates things slightly because there's more to the wave function than simply the spatial part of the wave function. But the essence of this is that if two identical particle wave functions overlap, the exchange symmetric combination gives, on average, a lower separation between the two particles, where the exchange antisymmetric combination, the one with the minus sign that gives you minus psi when you exchange the particles, gives a higher separation. And these are lower and higher compared to the case for distinguishable particles. This makes it look like there's actually some force between these two particles that has to do with whether our combination is exchange symmetric or exchange antisymmetric. This is why it's called an exchange force. Working with particles in the same quantum state, essentially, rendering them indistinguishable in an exchange symmetric way effectively attracts them to each other relative to their indistinguishable case, and combining them in an exchange antisymmetric way produces a slight repulsion. And the attraction or repulsion here, the amount the expected value of the separation changes, depends on how much the wave functions overlap. So if we have large overlap, you might expect this to be a very large effect, whereas if the single particle wave functions are separated by a large quantity, large amount, the overlap integral is going to be very small, and as a result, you will not see a very significant effect of this exchange force. Essentially, the likelihood that the particles could exchange places has, tells you how big an effect this exchange force exerts. One example where this is very important is in the hydrogen molecule, H2. In H2, we have, say, a proton and another proton. And if you want to think about things along an axis, separating these two particles, our electron wave functions are, for instance, going to look, if I plotted them simply like that, they're going to look something like this. Now this is a very crude representation of the wave functions. Obviously, I'm only looking at them in one dimension, whereas in reality, you know these are going to be three-dimensional wave functions. But the picture that I'm trying to paint here is essentially two n equals 1, L equals 1, M equals 0, n equals 1, L equals 0, M equals 0 orbitals, the ground state orbital for the hydrogen atom, overlapping with each other. And this overlap region here means that we have some possibility of exchange. So if I have the plus sign, the exchange symmetric combination, that means my electron separation will be low. The separation between my two electrons, the expected value of x1 minus x2 essentially. That means that the electrons are likely to be found with a small separation. In the region where the electrons are likely to be found with small separation, the region where the electrons have small separation is in between the two protons. So the electrons are concentrated between the protons. That means that we're going to have an effective negative charge density in between the two protons, and that will act to attract the protons together. On the other hand, if I'd used the minus sign for the combination, I have an antisymmetric underexchange wave function, then you know that's going to give me a higher separation. The electrons are going to be concentrated away from the center. You actually have then a deficit of electronness, a deficit of likelihood that the electrons will be found near the center, and that tends to repel the protons. The protons repel each other because without electron in between them, they just see each other's charge directly, and they repel each other. In the language of chemistry, the exchange symmetric combination of these wave functions are called bonding electrons, and the exchange antisymmetric are called antibonding. So the combination of these orbitals with the plus sign is a bonding orbital, with the minus sign is an antibonding orbital. And it turns out that in order to have H2 as a molecule exist, you need to have a bonding electron orbital. Now, if you allow those electrons to bond, or if you have the bonding case, you need to have the plus sign in the exchange symmetry for the spatial part of the wave function. That's not possible unless we include spin, because electrons are fermions, and the overall fermion wave function has to be exchange antisymmetric, which means if the spatial part of the wave function is going to be exchange symmetric, the spin part of the wave function has to be exchange antisymmetric. So there is a connection between the spin of these particles and whether or not you can make bonds with them in a two-particle case. So to check your understanding, what I'd like you to do is reflect a little bit. Is this exchange force a real thing? It looks mostly like it's just a mathematical artifact and has to do with the expected values of things that you would never really be able to observe, since x2 minus x1, the separation of the particles, you can't exactly hold a ruler up to an atom and measure that sort of thing. But then it does actually have an obvious effect in terms of hydrogen atom, in terms of the hydrogen atom, whether you're talking about bonding electrons or antibonding electrons. So reflect a little bit on that. Just let me know what you think. Some other questions to consider. If the wave functions don't overlap, the exchange force effect disappears. I'd like you to explain that effect in the context of whether or not the particles are distinguishable. And finally, though I've said a little bit about this, think about how might the inclusion of spin affect the discussion of whether we're talking about bonding or antibonding electrons in the hydrogen molecule. State that in your own words. Sign or a minus sign, psi A x2 and psi B x1 will give me the same wave function, essentially, back if I swap x1 and x2. If I swap x1 and x2 here, I'll get psi A x2, psi B x1, plus or minus psi A x1, psi B x2. And that's essentially what we have here, essentially just swapping these two terms. If I use the plus sign, I'll get my original wave function back. If I use the minus sign, I'll get minus my original wave function back. And that minus sign does not affect any of the observables. Changing the sign of the wave function won't affect any of the outcomes of any of the measurements you could make. There is, however, one aspect of these combined particle wave functions, where the plus and the minus sign actually make a difference. Quantum mechanics being the physics of the very small, we have to deal with the behavior of very small things. One nuance of dealing with small things is that they're very difficult to distinguish. If I have an electron here and an electron here, there's really no difference between this electron and this electron other than their position. It's not that this electron has a distinct identity from this electron. The analogy that Griffiths uses is that I can't paint this electron red and this electron blue, or hire a private investigator to follow this electron around to make sure it doesn't exchange places with this other electron. And quantum mechanics has to respect that indistinguishability. If we're working with distinguishable particles, we can write wave functions like this. Psi of the position of particle 1 and the position of particle 2 as two arguments to the wave function, being, for instance, 0. But if I square it, I would expect there to be, on average, some squared separation between these particles. So we can work with this. This is an expected value. You can, first of all, you can expand it out. x1 squared plus x2 squared minus 2 x1 x2. And these are the terms that we're going to be working with. The expectation of the sum is the sum of the expectations. This is a property from statistics, if nothing else. So this gives us the expected value of x1 squared plus the expected value of x2 squared minus twice the expected value of the product x1, x2. So if we're going to evaluate this sort of expression for the expected value of the separation in these indistinguishable state psi a, the single particle state for particle 1, x1, multiplied by the single particle state psi b for particle 2, x2. This, however, is distinguishable. If I swap these particles, x1 and x2, by exchanging the coordinates where I'm evaluating this wave function, I'll get a different result. I'll get psi a x2, psi b x1, and that is in principle different than psi a x1, psi b x2. What we discussed in the last lecture was that we could construct construct wave functions for indistinguishable particles by making combinations of permutations of these distinguishable particle wave functions. For instance, our distinguishable particle wave functions psi a x1, psi b x2, combined with either with a plus. When we're making indistinguishable particles, the way we choose to make them indistinguishable actually does make a difference. And one way to see how see the difference between the plus and the minus signs is to calculate the expected value of the separation of the particles. This leads to something called an exchange force, and exchange forces are really an interesting nuance to quantum mechanics that has no classical counterpart. So let's consider calculating the expected value of the separation between these two particles. So expectation of x1 minus x2, and we'll have to square that, because if these particles are going to be indistinguishable, I can't tell which one is to the left of which. So the absolute difference, or the difference x1 minus x2 expected value, must go to